Hello everyone, welcome to the Lab 6A of our STM32C0 MOOC. This lab is the equivalent of the Lab 6, which has been implemented using the hardware abstraction layer. In this lab, we will use the low-level library. The low-level library is an unitary service function provided by STMicroelectronics, making the access to register easy. Hence, the optimization regarding the code size and the performances of the application. During this lab, we will have the opportunity to configure the ADC associated with the DMA and the timer of the STM32C0. To do this, we will use the low-level library as I said lately. Concerning the usage of the ADC, we will connect an input voltage on the pin PA12, which is the ADC1 input channel 12, and transfer the converted value from the ADC data register to a buffer located in the RAM, thanks to the DMA and timer, which will trigger the conversion at each second. Here we have the block diagram summarizing the use case that we intend to implement. As you can see, here we have the input signal that will be converted from the analog domain to the digital one by the ADC. After the conversion, the converted value will be transferred by the DMA from the ADC data register to the buffer located in the RAM, and the conversion will be triggered by the timer tree working as a time base. Regarding the working condition of the ADC, we will measure an 8-bit data through the pin PA12, and each second the timer tree will trigger the conversion based on its update event. After the conversion, the data will be transferred by DMA channel 1 from the ADC to the buffer stored in the RAM. Regarding the configuration of the DMA, we will use the channel 1 configured in circular mode using byte on both sides, meaning bytes on the peripheral side and the memory side. To implement our application, we will keep the same configuration as in the Lab 6, so no modification will be performed. We will keep the same parameters. So regarding the timer, we will set it as an up counter using an internal clock which will overflow at each second, providing the trigger source for the ADC. And for the ADC, we will set the input channel 12. After that, we will configure the resolution, enable the DMA, set a sampling time, and use the timer tree as a trigger source. We will keep the same also for the DMA. We will configure the mode in the circular one and set the data weight in byte. And regarding the increment address, it will be set automatically. So let's create a new project on CubeIDE. Here we will enter the part number of our product. So it will be STM32C031C6T6. So we have to click on next. And here we have to enter the name of our project and click on finish. So as I said lately, let's configure our timer tree. We will set the clock source in the internal one, and we will apply the same value as in the Lab 6. So here we have to put 11,999. The counter mode will be an up counter, and here we have to put 999. So regarding the trigger event selection, we will put it at the update event. Okay, and then you have to configure the ADC, enable the input channel 12, we will apply the same parameter as in the Lab 6, so the resolution will be 8-bit. Before enabling the DMA section, we need to add the DMA channel. So we will do it after. So here we will set the sampling time at 12.5 cycles. We will set also the external trigger source. We will put the timer 3. We will let the external trigger conversion edge as the rising one. And then we will add the DMA. We will put the mode in the circular one, and for the data wise we will choose byte for the peripheral one and the memory one. So we have to go back to the ADC settings, and here we have to enable the continuous conversion DMA request. All the previous configuration has been done based on the following clock configuration. So by default, the highest speed internal is used, and it is set to 12 MHz, and this one will feed the timer clock and the ADC clock also. So this section is the most crucial one. On this section, we will switch the drivers for each peripheral from the HAL to the low-level library. To do this, we will select Project Manager. At the admin settings, we will change the drivers for each peripheral. So let's do this. So here, as you can see, the clock is already set to the highest speed internal, so no changes are needed. So now we have to go to the Project Manager section, and in the advanced setting, we have to switch for each peripheral the driver from the HAL to the low level. So at this section, we will check that our project has been well configured regarding the project location and the project name, and after we will generate our project. For that, we have to go to project section, and you can see that everything is fine. Okay, now we have just to generate our project. After the generation of the project, we can open the main.c file to check if you are really using the low-level driver. As you can see here, in the initialization of the clock, we can see that the prefix LL is used. It is the same for all of these peripherals. We can check that for the ADC one. As you can see here, we have the prefix LL also. After generating our project, we will now implement our application. To do this, we will need to define, first of all, 3 constants. The first constant is a delay that we have to respect between the ADC end of calibration and the ADC activation. This value is related to the ratio between the CPU clock versus the ADC clock. For example, if this ratio is above 32, a higher delay is required. We will need also to define the voltage of our internal reference. On our board, the VRF pin is connected to the VDDA, which is also connected to our power supply. We will need also to define the size of our buffer. After that, we will declare our buffer on which we will store the converted value. We will need also 3 functions. The first function is the ADC calibration start. This one will start the calibration in order to reduce the noise related to the ADC gain and the offset error. We will need also to configure the DMA and enable the ADC. After that, we will start the timer counting in order to trigger the conversion at each second. So let's copy and paste this section of the code. First of all, we will copy the constants. So in give IDE, we will copy it here. Okay, let's copy the declaration of our buffer. We will copy it here, and then let's copy our three functions. We will copy it here. So for each function, we will provide some details related to its implementation. Regarding the ADC calibration, first of all, we will need to disable the ADC, and then we will enable the internal voltage regulator. After that, we have to wait a stabilization time, which has been defined in the datasheet. So whenever we have an ongoing DMA transfer request, we will disable it, and then we will run the ADC calibration on itself. We will need to wait till the end of the calibration of the ADC, and then we will restore the DMA transfer request. So all of these steps has been defined in the reference manual. Here we have the implementation of the ADC calibration start. All the steps that I highlighted lately has been implemented here. So let's copy this function. We will copy this function in the user code begin for. Okay. So regarding the ADC DMA configuration, first of all, we have to set the source and the destination address. After that, we will need to define the number of data that we have to transfer, and then we enable some interrupt. The interrupt related to the transfer complete, the alpha transfer, and the error transfer. After that, we will need to enable the DMA channel, and then enable the ADC and start the conversion at the end. So all of this step has been defined in the reference manual, so we recommend to glance at this related section. Here we have the implementation of the ADC DMA start. We have just to copy it at the related section. Let's do that. At the same section. Here we have the function that will enable the counting of the timer tree. So we have just to write 1 in the C in N bit. So it's a simple function. Let's copy this function. So now we have just to compile our project. As you can see, everything is fine. Now we have just to call our function in order to perform the conversion of the ADC. To do that, we will call its function here. So first of all, we will call the ADC calibration, and then we will call the function ADC DMA start, which is here. After that, we have to start our timer. Now we can compile our project. So our project is ready to run. Now we will run the debug in order to check if our ADC is working correctly. So our debug has been launched. So let's add the buffer in the live expression section. Okay, so now we have just to click on resume, and as you can see, at each second we can catch a sample. Given that the input channel 12 of the ADC is floating, we are getting some random value. So now let's apply real voltage. We will apply the 3.3 voltage. And as you can see, we are getting 0x FFF, which is the maximum value. We can connect it also to the ground, to the GND pin, and then you can see that we are getting 0x0. So we can say that our ADC is working correctly. Thank you for watching. Bye.